Hi, welcome to the Signal Path. In this episode, we're going to try another repair. This is a Rohde Schwarz FSL Spectrum Analyzer, 9 kHz to 6 GHz. It's actually a fairly old unit, even though it doesn't look like it. It runs Windows XP, and there's something wrong with it. We're going to have to take a look. And yes, I know it's not the front panel connector. It's definitely something much more serious. So let's turn it on and see what it does. And here we go, 2 minutes later or so, and we're in the firmware, and this does not look right at all. The noise floor of a spectrum analyzer is fairly white, especially within a small frequency span like 100 megahertz we have over here. So let's look at a larger frequency span. Let's go from start of 0 to stop of 6 gigahertz, which is the full span roughly. Here we go. Yep, that looks pretty bad. There's a lot of spikes here at low frequency. We have huge tones. So something is seriously wrong. So let's figure out if we can see if the instrument is generating any errors internally. Let's go to, let's say, system info, system messages. Nope, nothing there. Okay, let's go under service. Let's run a self-test. I think this might take a little bit of time. And let's see. Okay, I already see a whole bunch of failed states. So now checking the LO. Oh, and the LO. LO is clearly unlocked. LO3 unlocked. That's a bad one. So it's going to be a fun one to figure that one out. But it's supposed to run a lot more tests, I think. All right, it's done. So CPU temperature is 41 degrees. That's fine. The entire thing has failed, of course. So we have a whole bunch of errors. Now, if I look at this, I would say, intuitively speaking, we have to analyze this one first, because a lot of these other tests that spectrum analyzers typically run, like alignment, checking for attenuation, checking IF stages, all of those things are going to require a present LO. If there is no LO, you cannot test all the mixers and down converters and digitizers and everything else inside of a spectrum analyzer like this one. So always, this is the first one we need to pay attention to. Now, there is no service manual that I could find, at least, or anything that has even a block diagram. So it's going to be a pretty fun one trying to reverse engineer essentially what's going on. It's going to be fun nonetheless, even if we can't fix it. But I think we're going to have to take it apart. So here's the inside of the instrument. All I've done is taken the cover off right now. This is the top of the unit. The front here is at the bottom. That's why I really like these bumpers. It allows you to put things down without damaging it, especially when you're taking the cover off. So there's a whole bunch of areas up here with cars that are not populated. This thing probably has maybe wider IF options, OCXO, maybe a real-time, and a whole bunch of other things that this is not populated with, but that's okay. A little bit closer look reveals that if you look at the RF connector, which is coming over here, it goes into this board. And the only other connection to this board is this ribbon cable in the back. So this is the entire spectrum analyzer from the RF point of view. This is common for kind of the entry-level spectrum analyzer architectures where everything is on a single board. Rohde Schwarz is quite good at that, but this will never have the performance, of course, of dedicated LO, dedicated IF, RF, front-end various frequencies with filters and so on. But that's okay. Of course, Rohde Schwarz does that with their higher-end spectrum analyzers, but this is probably an entry one. But so everything is in here, so we should be able to take a close look at it. If I spin this a little bit, there's really not much else. The rest of this is just a PC, basically. So I think the computer is right underneath this. I don't know if you really need to take a look at it. There's a fan over here. This fan is always running, even when the power is off. And it's probably because this fan is configured so if you have an OCXO or something else that's always powered on when you plug it in, that it will keep it at a steady temperature. A power supply up here, nothing really unusual aside from that. So we really need to pay attention to this guy. Now, if the ribbon cable over here is far too thin for this to carry anything more than potentially a 10 megahertz signal, maybe a 100 megahertz signal to some bus somewhere else, but I would imagine that the digitizer is in here. So this is carrying the digitized information of the spectrum. So we'll find out when we take it apart. Now, looking at this, we can probably take it out and disassemble it and even maybe even put it back, so we can probe it and analyze it while it's there, which is super convenient. If it was this way, it would be a lot more difficult, of course. So here's the board. Let's see what we have here. So I'm a little bit surprised at how few screws there are. Normally, you put a lot of screws on a board like this because you want to press down and really isolate the individual compartments underneath this, which have to be isolated from each other. It may be that they just didn't need to do that, so they don't need to put a lot of screws. But if you've seen any of the other modules I've opened in the past, that's typically the case. If you want really good isolation, you have to press down on those conductive layers between these things that are sandwiched to isolate them. So I'm going to remove this. There we go. Here's the different chambers I was talking about. And you can see the absorbers squished in. These are quite soft and conductive. All right, let's take a look at this. Looks quite nice. And here's our RF input right away. We can see that. And there's a unpopulated portion here. My guess is that this is the tracking generator. It's a little bit surprised that it's not populated, and there's a whole bunch of components here that are probably tied in with this that are not populated. Normally what they do is that they populate everything anyway, and then you enable something with a software option, and otherwise it's not there. For a tracking generator, the connectors and everything, yeah, it adds up to the cost and the components. That's probably why they haven't done that. So they run this in multiple versions, one with and one without it. Let's look at the other side. There we go. There's some RF absorbers here strategically placed into the chassis. Here we go. Looking really nice. So Rohde & Schwarz really loves this kind of design. You've seen it in a couple of different places. So here's the RF input, here's our AC blocking cap, some input protection over here with the diodes, and this section is quite important because you want to maintain a really nice, good characteristic impedance of 50 ohms. That's the impedance seen by whatever device under test you connected to. So you want it to be as good of a 50 ohm as possible. So if you look on the other side, you can see they've removed the metal in order to reduce the parasitic capacitance footprint of these components that they had to put on top. And here are the diodes, the 3 series diodes here as well, you can see them. So that's probably a fairly good input. We see a whole bunch of filters over here. A couple of connectors actually not populated. So this thing probably has a few other options. You can see some in the back here. Maybe for external board for the IF with higher bandwidth. That's probably what these are. So we know what the problem is. We know the issue is this LO unlock we need to look at first. We can go ahead and analyze this and reverse engineer. But the overall architecture of all these are fairly similar. They're all super heterodyne, multiple LO conversion stages. They do this for various reasons, which I have talked about quite a bit in the past. And some of these I see are Rohde & Schwarz branded chips, so we're never going to be able to find a replacement for these, and we probably won't even find a data sheet for them. But anyway, nonetheless, we can explore this. So let's find the core of the PLL. Let's go on the other side a little bit. Let me take a brief look here. Let's see. All right. Okay, so what I think is going on is that we have what appears to be a TCXO, that's 10 megahertz. That's going over here in this area. This TCXO is connected most likely to over here, and this is probably our VCO. I'm going to have to look at the part number. This looks like to be a Hittite part or analog devices part. It would kind of make sense because we have this output coming over here, then it splits into multiple directions. And one of it seems to be coming back over here and fed over to these regions. So I would say the PLL core is probably here. So we have to look at all of these components and see what these are. I have to do a quick Google search on them. And it might be that this one, which is also looks like a part number that we're not going to be able to find anything about, this one is probably also a Rohde & Schwarz branded part. And I think there's more than one of them. Yeah, there's another one here, another one here. Interesting. So it's probably multiple synthesizers. We have to take a closer look to figure that out. We see there's actually 4 of them. That's even more interesting. Okay, we'll figure it out. No worries. Here's our analog to digital converter. So just as I thought, we have our final digitizer here. So that's the data. Here's the ribbon cable on the other side of this. You can see all these interfaces to it. So they're grabbing the data from that. We'll take a look at the data sheet for this as well, probably only tens of megahertz or so. A couple of Atmel devices over here. Here's a whole bunch of switches. So this is probably where the input comes in and gets split into multiple different bands, and those bands are what are responsible for different conversion stages depending on what input frequency you have. Some switches here. This is probably an attenuator, programmable attenuator. This is most likely a mixer over here, one of the main mixers of this instrument. Yeah, looking good. Okay, so that was kind of an ad hoc analysis. We have to take a closer look, but I'm going to also do an X-ray of this just so that we can have them side by side in case we need it. And then we will trace out the LO signal and measure it one step at a time. All right, I think we're getting some really nice looking X-rays here. And here we have the photograph of the board and of course the X-ray, so we can now see everything. And here's the picture of the other side of the board and lined up with the one, so we can really understand what's going on and what's connected to what, which would help to figure out what the issue is actually. So let's look at the front here. You can see the signal coming in, and indeed it does wrap around and goes through this front-end filter. And this filter is a low-pass filter up to 6 gigahertz, eliminating anything above 6 gigahertz so that it doesn't fold back onto the IFs of interest. Remember, these are super heterodyne, as I said. They up-convert and down-convert, and if you have frequencies that are present where they shouldn't be, even if you're not interested in them, they will overlap with the IFs and it will cause a whole bunch of problems. You can see a whole bunch of LO filtering over here. These are the different LO bands so that you can have a single pure tone coming in from the synthesizer. There's a lot of, it's quite compact actually, very difficult to follow even with an X-ray. Here we have some front-end switches and a digital attenuator. You can see it on over here. There you go, these devices right over here. And then we go back over here a little bit more into this section. Now this is probably the most interesting part of this, at least in my view. If you look at this structure, it's quite unusual. We have the LO, I believe, coming over here, and there's this amplifier here. This is a 6 to 13 gigahertz amplifier. So if I go to the other side of the board, that's the section. Look at that. So the signal comes over here, amplified, and goes into this feed line. And this feed line is basically almost like a probe feed into the substrate. So it's transmitting into the substrate. You're going to have some backing on the other side of this in the chassis, which we did. And that has to couple to something on the other side. Now, if you go back to the other side, you can see that coupling structure over here, and there's a bit of RF absorber over here as well. It almost looks like a Vivaldi structure, where that feed line couples directly into it and probably excites it differentially. And that gives you an LO differential feed into this mixer. On the other side, it looks like the RF and the IF, I should say, are actually shared with each other. So they're both at very high frequency, so you can couple into it. This is, I think, what's going on. It needs a bit more analysis, but at first look, that's what I believe is going on. Very interesting structure. Probably back then, this was the highest frequency component here. After this, everything then gets down converted, I believe. So that's it also gives you some filtering, by the way, when you make a structure like that. So quite interesting, might be worth simulating and talking about in a separate video. And then we go further down over here. There is another mixer down here. This is our second mixer, I believe. Where is that mixer? Here you go. There it is. It's also from Hittite or Analog Devices. If you go back a little bit again, try to follow the part of the PLL, which is the problem we're trying to look at. This guy over here is our VCO. This is a 3.1 to 3.5 gigahertz VCO, again from Hittite. You can see the signal coming over here, it gets amplified, and then it gets split into multiple places because you need to feed different sections and even divide them and get to the other mixer so that you can get the final IF. And if I look here, you can see some of it coming back over here, feeding onto this side. And I looked at these components a little bit more carefully. There's actually a divider here, which is necessary. It was a little bit puzzling because I was not looking at this very carefully originally. And I looked at this component over here. This is our phase frequency detector. But this phase frequency detector was only rated up to about 1.5 gigahertz. So you couldn't connect the VCO directly to it, of course. So I was looking for that divider and eventually found it. That's over here. It's a divide by 4. So the signal coming over here is coupled into multiple places, and some of it right over here is coupled back through here into this, and then this eventually finds its way over here. Here's a reference over here that also finds its way to here. This is most likely a synthesizer chip then and works with this phase frequency detector closing the loop of the PLL. So this is where I would probably pay attention to. Any of these components in the chain can totally mess up, of course, the synthesizer. And there's a whole bunch of other filtering over here, some lower frequency filtering. These are inductors, of course. And yeah, we could again go through every little bit of this, but I think for now we have enough information to at least begin studying this LO section. Make sure we do have our 10 megahertz, make sure we do have our VCO actually working, and we do have power supplies and signals coming into the phase frequency detector. These are the places that are worth paying attention to. So let's go and reassemble this, and then we can make measurements live on the instrument. Before we do any RF measurements, we can just do a couple of quick power supply measurements to make sure none of those are missing on some of these critical PLL components. So I'm going to ground over here. Let's measure the power supply of our VCO, which if I'm not mistaken is here. There you go, 3.3 volts. That looks good. So our VCO definitely has power. Check the power supply of our TCXO, 1.5 volt. Looks good. Those are the main two things I wanted to check. Those are the main ones I'm going to measure right from the beginning. Now, if I look at the tune voltage of the VCO, when the instrument is running and constantly trying to lock, we should see a jump all over the place. If the rest of the PLL is at least doing something, here's the tune voltage. There you go, look at that. It is definitely jumping all over the place. You can tell from the fast bar update at the bottom. We can in fact put this onto some AC voltage. I'm going to hold this, turn this into AC. We should see some AC activity. The frequency is going to be high. Some of the low frequencies might be cut. There you go, see? There's AC voltage there. And that's because the PLL is trying to lock continuously. So since the VCO has some tune voltage on it, I think it's a good time to take a look at it in the RF domain. So in order to snoop on the RF signals without interfering with the signal flow there, we're going to use this anti-kernel probe, inexpensive probe, which I reviewed in one of the previous videos as well. We're going to combine that with the Rohde & Schwarz ZNL6, which is a hybrid instrument. Also, I've done a complete teardown and review of that instrument too. So with this, we can, using this ground signal tip, we're going to monitor different voltages along the signal flow and see what happens to the PLL in its operation. So I'm going to zoom in here. Look at this tone over here. That tone is from my wireless microphone being picked up. Okay, so let's go ahead and land directly on the VCO output. Now, what do we expect if the VCO is working? First of all, we expect the signal around 3 gigahertz, but we also expect that signal to be jumping around quite a bit, because we saw that the tune voltage of the VCO was jumping around because the PLL is trying to achieve a lock. So that's kind of what we're looking for too. Now, there's a difficulty here in landing, so it's not going to look very good at the beginning. Now, one thing to also keep in mind is that this big signal you see here, this is at 548 megahertz. That's my wireless microphone. You're going to have to ignore that one. All right, here we go. So here's our signal. Let me get the ground. There it is. Look at that. That's exactly what we see. This is a 3 gigahertz signal. This is a 6 gigahertz span. So in the middle, right, roughly around 3 gigahertz. And indeed, we have a signal jumping all over the place as the PLL tries to lock, and it's within the frequency specification of this IC, about 3 to 3.4 gigahertz or so. That's great. I think the VCO is working. Now we can follow that signal a little bit further down to see if it makes it past, let's say, the first amplifier or the first, actually this is the first attenuator here. Let's see if it gets past that signal. There it is. Yeah, still present. Good. You can see some second harmonic over there too. Let's go to the input of the divide by 4, which I think is here. There we go. It's still there. Input of the divide by 4. Looks good. Now the output of the divide by 4. If I can land on that, that's a difficult spot to grab. Here we go. I have to get rid of all that low frequency noise. That means the ground is not connected. There you go. Okay. So there's a lot of tones here, but it doesn't look good. So again, ignore this one. That's my wireless microphone. Here's the feed-through signal. That's our 3 gigahertz signal feeding through the divider. That's normal. But I don't see an equivalent signal around 750 megahertz, which is also moving around. If this divider was dividing correctly, you would see a signal jumping around correlated with this one at 1/4 of the frequency. But there's absolutely nothing there. Either I'm probing it incorrectly or something is wrong. Interesting. Okay, I'm going to have to investigate this a little bit further. Here's the input again. You can see jumping around. Again, this probe has a huge attenuation, so don't look at the numbers on the left side on the axis. Let's see, going to the output. Once again. Yeah, it's not there. All right, let me investigate this a little bit further. It's a bit strange. So let me show you where I measured just so that we're on the same page. So here's the output of the VCO. I measured here between this ground and this point. You saw the signal. I measured here. It was fine. And then if you look, it couples from here into here, and it goes into the divider. So I measured here on the input of the divider. The signal was smaller, as to be expected. There's an attenuator here. And then I measured at the output of the divider, which is coupling into this capacitor, into here, into this amplifier. I should measure after the amplifier too, but I measured between this port and that ground on the other side. And indeed, I saw nothing. And so, a little bit strange. I mean, this is all passive from here to here. It's very unlikely that that's the problem. And anyway, this will couple anyway at 3 gigahertz. So I worry that this might be dead. It could be one of our problems. The other problem could be that I could just be mistaken and the signal here is not very large and it's needed for here. Although I doubt that. We have to look at the data sheet of this part. So I'm just sharing with you my thought process. The signal from this, once it's get divided out, going through here, I have to trace it out, and it ends up all the way up north where the phase frequency detector is, which I think I can show you. Where is the phase frequency detector? I think that's right here. And I think that couples into this. You can see this transformer here looks like takes the 10 megahertz signal from here, feed it into this, or sorry, feed it back into here, and this is controlled by this. This is just my guess. But either way, it's a little bit unusual. I wasn't quite comfortable with what I was seeing here. So let me investigate it a little bit more. So I may have found something really unusual. So hopefully you can see everything at the same time. So I'm going to measure the power supply going on to the divide by 4 circuits. We already measured the power supply of the VCO. That one's okay. So here's the power supply going into the divide by 4 chip. Look at that. 0.7 volts. That's not right. But the power supply is coming from this component here. That's just a resistor. You can't see the part on it. It's a 1 ohm resistor. So it's basically a short circuit. If I measure on the other side, look at that. On the other side is 3.3 volts. Now on the other side of the resistor, it's 0.8 volts. That makes no sense at all. Obviously, that's not due to current, because you're going to have an enormous amount of current through a 1 ohm resistor to make that kind of voltage drop, and that resistor would be on fire. So is the resistor bad? But then why would the resistor go bad? The reason I'm worried, and I still think the divide by 4 may be the fault, because this 1 ohm resistor is typically used like a fuse, basically. So if that divide by 4 somehow becomes a short circuit, the fuse basically, the resistor burns up and disconnects it so that the rest of the circuit doesn't get damaged, and you don't have to put a fuse in, which is quite a bit more expensive than a 1 ohm resistor and also quite a bit larger. So it may very well be that this divide by 4 is dead and that has blown out this resistor completely. So we're going to have to investigate a bit more. So here we go. What I did is I removed the resistor, which was right over here, and I also removed this capacitor, and I'll explain why that is. I did that after making a few measurements here. So the goal is I'm going to put my ammeter across this resistor, essentially forcing the current that used to go through the 1 ohm resistor to go through the current measurement, and that allows us to power this on safely through that and figure out what the power consumption of it is. If the current flowing through it matches a datasheet for this part, then this part is probably not damaged to begin with. So let's do that experiment. Okay, so the multimeter is in the 10 amp range so that we don't have to worry about burden voltage or anything like that. The instrument is powered on. Let's go ahead and measure the current through this carefully. There we go. 65 milliamp. Okay, so I'm going to put up the datasheet for this on the screen. And if you look at the bottom right on the table, you can see that this is well within the power consumption of this device at 3 volts. And they're running it here at 3.3, and there was a 1 ohm resistor there, so there's some drop and so on. Okay, so that looks good. So I don't think the divider is at least the problem here. So we're going to have to put another 1 ohm resistor back, and let me tell you what happened with the capacitor. Okay, so here's the original resistor at the top, and there's a capacitor that used to be here, and there is now a new resistor and a new capacitor in this place. So what ended up happening was I was trying to measure the resistance across this frequency divider to see if there was a short across it from its power supply to ground. And I was probing around this capacitor, and I noticed that sometimes when I pushed really hard against the capacitor to make a good contact, the resistance I was measuring would go from 5 ohms to 200 ohms. It would jump back and forth. And of course, 5 ohms is very, very small. So what I think was going on was that there was a flaw inside this capacitor, potentially an ohmic contact, causing maybe 10 ohms or so. And that was causing the entire structure to draw a lot of extra current in order to supply the current for the frequency divider as well as the current DC current that was going through the capacitor. And that over time heated up and aged this 1 ohm resistor, and I think it eventually died. When I took the capacitor out, it wasn't measuring any resistance anymore, and it's probably because I heated it up a lot and whatever flaw was in it might have cleared. It wasn't measuring a good capacitance to begin with. So I think that's probably the cause of failure, considering that this frequency divider, I think it's still okay. I haven't powered this on yet, so let's go ahead and put it back inside of the instrument and see if it does anything at all. Okay, let's go ahead and do our probing measurement one more time. Let's go back to the output of the VCO, and let's see what we see here. If I can probe it properly. Here's the output. Look at that. This is the 3 GHz signal. Look how steady that is. That already tells me that the PLL is locked. That's why the signal is not moving around. The synthesizer itself is at a fixed frequency in this situation. There's no sweeping. So look at that. Yeah, it is locked. Let's go to the output of the divider and see if we see a signal at all now. There we go. There it is, right there. The one next to it is my wireless microphone. You can see if I move it around, the tone goes up and down. But yeah, the divider is now producing. You can see all the harmonics of the divider. It's probably putting out a fairly nice square wave coming out. Looks good. This is very promising. Now we have to close the whole thing back up. All right, check this out. The spectrum already looks a lot nicer, but of course we have to do a complete self-test. So we're going to do that again. If we go into service functions and we run a self-test, and let's let this run for a bit and see what happens. And unsurprisingly, of course, everything passes because we have a complete self-test going on, and then now that the LO unlock condition has been repaired, all the other tests also pass. We talked about this. Without the LO, you cannot run all the other tests anyway, so they all come back as failure. Looks very good. Now I want to test it, of course, with an input signal. So in order to do that, we're going to connect it to a synthesizer. Unfortunately, I do not have a Rohde Schwarz synthesizer that goes up to 6 GHz directly, and hopefully that'll change in the future. But right now, we're going to test it using the Keysight MXG. So that's going to generate up to 6 GHz tones for us. Okay, so here's a trace on max hold. We're looking at a 500 megahertz signal. So let's go to 1 gigahertz. There you go. Here's a 1 gigahertz signal. I'm just going to go through everything about 100 megahertz at a time to see the entire spectrum. And here we go. Looks nice. You can see there's a little bit of ripple. There's a bit of drop across from DC to 6 gigahertz. That's normal. I'm using a fairly low quality SMA cable right now. Yeah, I think it looks good. And there you have it. I hope you enjoyed this repair. Thanks again to all my Patreon supporters for making all this possible. I'm working on a pretty cool video after this one, which is also suggested by the Patreon supporters. So I think you're going to enjoy that one. That's a much, much higher frequency stuff. And if you have any question, let me know, and I'll see you in the comment section.